If I asked you what a star is, what answer would you give? You might point to the sun and say, that's a star. Or you might go out at night, look at the sky, and say that every little dot of light you see is a star. And you wouldn't be wrong, but we can get way more specific than that. A star can be defined as an approximately spherical body of plasma. This body is held together by its own gravity and prevented from collapsing by the energy it generates by fusing hydrogen into helium at its core. Stars come in a very wide variety of sizes, temperatures, longevities, and many other aspects. The bigger and hotter stars have the shortest lives. It's said that massive stars live fast and die young. Of all of the stars that exist in the universe, and there are estimated to be up to a septillion of them, only a very small percentage are visible to the naked eye. But most of the light and radiation that we can observe comes from stars. Many can occur in pairs, multiple systems, or even star clusters. In this video, I'll be giving you an overview of stars and how they generally exist. This will also serve as the first entry in my new series on stars, and following videos will focus on individual stars that are in some way interesting or important. So, without further ado, let's learn about stars. For pretty much as long as we've existed, we humans have been looking at the stars. They've been important to things like religion and navigation, and it might not be inaccurate to say that astronomy is one of the oldest sciences. For a really long time, all we could do was look at the sky and record the objects we saw. But in the 17th century, the invention of the telescope and the discovery of the laws of motion led to a realization. Stars, all those tiny little points of light in the sky, they're like the sun, obeying the same laws of physics. The 19th century saw the introduction of photography and spectroscopy. These made it possible to investigate the composition and motions of stars. This was basically the birth of the field of astrophysics. In 1937, the first radio telescope was built, allowing astronomers to see radiation that was otherwise invisible. And in 1961, we saw the first gamma-ray telescope. Also in the 1960s, astronomers began infrared observations using balloon-borne telescopes. The first proper infrared telescope was launched in 1983. In 1992, microwave emissions were studied for the first time with NASA's Cosmic Microwave Background Explorer. 2 years earlier, the Hubble Space Telescope was launched. It's still active today and provides a deep, detailed view of the universe in visible light. In the years since, there have been even more powerful telescopes that can see in all wavelengths of light, and even more are still planned. Stars can be given a name in a few different ways. One method uses the constellations they're a part of. The IAU officially recognizes 88 different constellations. Usually, the brightest star in a constellation has the word alpha as part of its designation, and the second brightest is designated beta. This continues until all of the Greek letters are used, and after that, numeric designations follow. Some stars have had a name for hundreds or even thousands of years. Betelgeuse, for example, means the hand or the armpit of the giant in Arabic. It's the brightest star in the constellation Orion, so its scientific name is Alpha Orionis. Over the years, different astronomers have compiled star catalogs that use unique numbering systems. The Henry Draper catalog provides a spectral classification and rough position for over 200,000 stars. It's been widely used by astronomers for over half a century. In this catalog, Betelgeuse is designated as HD 39801. For newfound stars, the IAU uses a different system. Most names consist of an abbreviation that stands for either the type of star or the catalog that contains information about it. This is then followed by a group of symbols. For example, PSR J1302-6350. The PSR means the object is a pulsar, and the letter J reveals that a coordinate system known as J2000 is being used. The two groups of 4 numbers are coordinates. If you ever see a star with a name that looks like just a bunch of letters and numbers, it almost certainly means something. It can just be a little tricky to decipher it. Stars usually form from large clouds of gas and dust known as molecular clouds. These regions are cold, which causes the material to clump and create high-density pockets. Some of these clumps then collide with each other, or otherwise collect more matter. As the mass of these clumps grow, so does their gravitational power, and they sort of just keep collecting more and more and more. Eventually, the clump reaches a critical mass, which causes it to start collapsing under its own gravity. This marks the formation of a protostar, which is a little baby star. Over time, a protostar will use up much of the gas and dust from its original molecular cloud. Eventually, it generates sufficient temperature and pressure at its core for hydrogen fusion to begin. This is where hydrogen atoms are squeezed together to form helium, and this releases a ton of energy that keeps the star from collapsing under its own gravity. As mentioned at the start, the greater a star's mass, the shorter its life will be. A star that is actively fusing hydrogen into helium is known as a main sequence star. Currently, the Sun falls under this category. A star's gas provides its fuel, and its mass determines how quickly it runs through its supply. More massive stars must burn their fuel at a higher rate to keep themselves from collapsing. Some low-mass stars, on the other hand, will stay in the main sequence category for trillions of years. In fact, it's calculated that no low-mass star has ever died because the universe just hasn't existed long enough. Astronomers calculate that these stars, known as red dwarfs, will never fuse anything other than hydrogen. A star's fuel doesn't last forever, and eventually, it runs out of hydrogen to fuse. At this point, the core starts to collapse, but this collapse also increases the core's temperature and pressure, which makes the star start to puff up. Beyond this point, the late stages of a star's death depend heavily on its mass. Let's look at low-mass stars first. After all of the hydrogen is used, gravity crushes the mass of the star down. As the core heats, the outer layers expand and cool, and the star has now become a red giant. In the core, helium begins to fuse. Once that helium is gone, the core contracts and becomes even hotter, expanding the star once more and making it even bluer and brighter. The outermost layers are blown away. Now, all that's left is a remnant core known as a white dwarf. Over billions of years, the white dwarf will cool and eventually become a black dwarf. Now, let's take a look at stars with a higher mass. More massive stars will continue fusing heavier and heavier elements. Carbon, oxygen, neon, magnesium, and so on. For the largest stars, this chain continues until silicon is fused into iron. The next step would be, in theory, to fuse iron into something even heavier, but to do this would require adding energy instead of releasing it. The star has officially run out of fuel, which means there is no longer anything stopping it from collapsing. So, the core collapses until the atomic nuclei push the brakes and it rebounds. A shock wave travels outwards through the star, resulting in an explosion known as a supernova. If the remaining stellar core was less than about 3 solar masses large, it becomes a neutron star, an object made almost entirely, or just straight up entirely, out of neutrons. And if the stellar core was even more massive than that, there is no known force that can support it against its own gravity, and it collapses into a black hole. There are a lot of aspects that are used to categorize and classify stars. First, there's the star's brightness, which depends on its size and surface temperature. This is described in 2 different ways: magnitude and luminosity. Magnitude is based on a scale that's more than 2,000 years old. Greek astronomer Hipparchus numbered stars by their brightness as seen from Earth. The first magnitude labeled the brightest stars, the second magnitude the second brightest, and so on. The scale went up to the 6th magnitude, which included the faintest visible stars. Nowadays, the magnitude scale is a bit different. There's apparent magnitude and absolute magnitude. Apparent magnitude is how bright a star looks from Earth. Absolute magnitude is defined as how bright a star would appear to be if it were 10 parsecs from Earth. This is because a more distant star will appear dimmer even if it's objectively brighter than a closer star. The magnitude scale has also expanded, running from greater than 6 to even descending into the negative numbers. The lower the number, the brighter the star. Then there's luminosity, which is the rate at which a star emits energy. It's a more objective measure than magnitude, and it's measured in terms of luminosity luminosities of the sun. The color of a star depends on its surface temperature. A star might appear to have one single color, from blue to white to yellow to red, but stars actually emit a broad spectrum of colors. This even includes wavelengths of light that aren't visible to the eye. Different elements or compounds absorb and emit different wavelengths of light. So by studying a star's spectrum, you can determine what its composition might be. The temperature of a star is measured in kelvins. A star's surface temperature depends in part on its mass, and it can affect its brightness and color. The luminosity of a star is proportional to its temperature to the fourth power. So if two stars are the same size, but one is twice as hot as the other, the former would be 16 times as luminous as the latter. A star's size is measured in terms of the sun's radius. Some stars can be extremely small, like neutron stars, and others can be extremely large, even up to 1,000 times the diameter of the sun. Like a star's size, its mass is also measured in comparison to the sun, specifically in solar masses. It's important to remember that two stars of similar mass aren't necessarily of similar size because they could have different densities. Stars generate magnetic fields. When it comes to the sun, this magnetic field can become highly concentrated in specific spots. This creates features like sunspots, flares, and coronal mass ejections. There's also evidence of similar phenomena occurring on other stars. The average stellar magnetic field increases with the star's rate of rotation and decreases as the star ages. Metallicity is a measure of how many metals a star has. For this purpose, metals refers to any elements heavier than helium. This measurement is used to separate three different generations of stars. Population 3, the oldest, is technically theoretical because astronomers haven't actually discovered any stars that fall within it. This group was born in a universe without any metals. When they died, they released heavy elements into space. The next generation, Population 2 stars, incorporated these materials in relatively small amounts. Then, when a number of Population 2 stars died, they released even more heavy elements. That led to Population 1, the newest generation of stars, which contained the highest amounts of heavy elements. For most of a star's life, it's a main sequence star consisting of a core, radiative and convective zones, a photosphere, a chromosphere, and a corona. The core is where nuclear fusion takes place to power the star. Radiative zones are where the energy from nuclear fusion is transported outwards by radiation. By contrast, in convective zones, the energy is transported by roiling hot gases. The exact positionings of the radiative and convective zones can vary between stars. In some, the radiative zone is closer to the core, and in others, the convective zone is closer to the core. The photosphere radiates visible light and is often referred to as the star's surface. The chromosphere is a region that looks a little reddish because of hydrogen. And finally, the corona is the outermost layer of a star's atmosphere. Stars are typically classified by their spectrum using the Morgan-Keenan system, also known as the MK system. By this system, they're classified according to their temperature. Each category is given a letter. From hottest to coldest, these categories are O, B, A, F, G, K, M, and L. Within each class, there are 10 spectral types, ranging from 0 for the hottest to 9 for the coldest. Stars are also classified by their luminosity, which is given in Roman numerals. From highest to lowest luminosity, these are 1A, 1B, 2, 3, 4, and 5. The complete MK designation includes both the spectral type and the luminosity class. For example, the Sun is a G2V, or 5, star. As mentioned before, a main sequence star is one that is still fusing hydrogen into helium. All stars go through this phase of their life. Red giants are stars many times more massive than the Sun that ran out of hydrogen and are now fusing helium. In about 5 billion years or so, the Sun will become this type of star. White dwarfs are the remnant cores of red giants that have shed all of their outer layers. These objects produce no new heat of their own and just gradually cool over billions of years. In about 10 billion years, the Sun will become a white dwarf. Neutron stars are incredibly dense objects made mostly or entirely of neutrons. They form when a main sequence star with between around 8 8 and 20 times the mass of the sun runs out of hydrogen. The star fuses heavier and heavier elements until it goes supernova. Pulsars are neutron stars that rotate extremely rapidly. They have bright X-ray hotspots that spin in and out of view like the beams of a lighthouse. Magnetars are neutron stars with insanely powerful magnetic fields. Red dwarfs are the smallest main sequence stars. When one of these produces helium, the released energy brings material to the surface. Here, it cools before sinking back down towards the core, and when it sinks, it brings a fresh supply of hydrogen. Because of this constant churning, red dwarfs will take trillions of years to burn through their hydrogen supply. This means that there probably haven't been any red dwarfs that have died during the universe's current lifetime. Lastly, we have brown dwarfs, which aren't even stars. They're generally between 13 and 80 times the mass of Jupiter. These can be described as failed stars because they just never gathered enough mass to spark fusion in their cores. A lot of stars don't exist on their own. There are binary systems where two stars orbit each other, but stellar systems with as many as 7 members have been found. Some multiple star systems even host planets. Binary stars come in a lot of different varieties. Some binary partners evolve rapidly into giant or supergiant stars, while their smaller companions remain more stable. Pairs of neutron stars can spiral together and collide to produce some of the universe's heaviest elements. From our viewpoint on Earth, some binary stars even stage their own eclipses. These are valuable for determining the star's masses, diameters, precise orbits, and even their compositions. And that about does it for this needlessly long introduction to stars. As I mentioned at the start, this will be my first video in a series on stars. If there's a star you'd like to see me make a video about, let me know and I'll add it to my list if it's not already on there. Thank you very, very much for watching. Leave a like if you enjoyed and subscribe if you want to see more. I appreciate you being here and I hope to see you next time.